Okay, guys, previously we have shown that essentially our class 1 stocks, those good stocks identified by our decision tree model does perform better than the class 0 stocks. So those bad stocks identified by our decision tree classifier. Now let's get to optimize the model. So when optimizing the model, like before I go into the codes, one thing I want to emphasize is that so when we are optimizing the model, we are trying to find the optimal hyperparameter actually. And for that optimizing process, we also call it as fine-tuning. And the thing I want to emphasize is that whenever you are doing fine-tuning, you don't want to use a test set. Instead, you only want to use a training set. So because you don't want your algorithm to have an early pick into your test set, because we rely on the test set to create out-of-sample performance. But if your algorithm had an early pick into the test set, then you can no longer generate out-of-sample performance based on that test set. Now let's get to the code. So as usual, we create an empty list first to store the results. So we let optimal to be equal to an empty list, and then we start a loop. So here, the hyperparameter we're trying to tinker with will be the maximum depth level. So max depth. And here for the loop, we are looping in the range between 1 and 8. In other words, from 1 to 7, because as you guys have already know, for Python, it always stops one number ahead whenever you are using the range. Because we are using range 1, 8, therefore we are stopping at one number ahead, which is 7. So inside the loop, we are creating a classifier. So we are instantiating the classifier, meaning that we are creating objects based on the template, based on the classes. The CLF, the decision tree classifier, will just be equal to tree.decision tree classifier. So tree is a module. Tree is a module from the sklearn. And also for decision tree classifier, that's just a class name for our decision tree algorithm. Then we set the maximum depth. So the max depth to be equal to depth. So for example, if we are in loop 1, then the max depth here will be equal to 1. And if we are in the last loop, loop 7, then this hyperparameter is just going to be 7. Then we are just running 10-fold cross-validation for each of the loop, for each of the maximum depth value. So we specify a new variable called as k-scores, and we let k-scores to be equal to cross VAL score. And the first input is going to be our CLF. So that's a classifier. Then the second input is going to be X-train. The third input is Y-train. And as usual, the fourth hyperparameter CV, that's just the number of folds. So that's just K for the K-fold cross-validation. So it's equal to 10 here. And then the desired average score from the K-fold cross-validation is just the mean of the K-scores, meaning that it's K-scores domain. And here we are also appending the depth level as well as the average accuracy score, the corresponding average accuracy score to the list called as optimal we created at very first. So pretty much the optimal list here will be storing the depth level we tried out and also the corresponding accuracy score from cross-validation for each of the depth level. So that's the optimal list. And here we actually further transform the results into a data frame. So we use PDDO data frame to transform the optimal. And also we set the column names to be tree depths and also accuracy. And we are setting the index as a depth level. Then we also plot that data frame out. And we set the title of the figure to be hyperparameter tuning. The label of the x-axis being tree depths. So that tree depths. And the label for the y-axis is 10-fold average out of sample accuracy. Let's execute that cell. Now, let's just wait a bit for the execution here. While the code is running, let me expand the next cell here. So for the next cell, this IDX max, that's just going to return us the index, like of the highest element in a column. So that's going to be our fifth element. If the execution is completed here, then we will find out that the optimal depths will occur at index 5, which is actually just corresponding to the depth level of 5. So because previously we are setting the depth as the index, remember? Uh, oh, yeah, it's already like the execution is already completed. So we can see that basically the highest accuracy will be occurring at the depth level equal to 5. So let's execute this cell. Yep, our OPT depths will be equal to 5. Yeah, I'm just scrolling back to the model with the depth level of 3. So because in later cells, we're just comparing that depth equal to 3 to depth equal to 5. Let me check that first. Now let's continue with this optimized hyperparameter here. So we find out that the optimized hyperparameter is 5. Then we just want to check, does our optimized model perform much better than the original model with depth of equal to 3. Now, what we did here was just training based on the training set. Of course, for this new classifier, this CLFOPT, we are setting the maximum of the depth level to be equal to the optimum level we just found out. And we are fitting the classifier to the training set. And then as usual, we generate the out-of-sample predictions using the test set. So using X test. And the out-of-sample predictions is stored in Y test prep. And then we use that out-of-sample predictions to calculate out-of-sample accuracy. So we are using the accuracy score from matrix module. And for the first input, that's going to be the actual labels. And the second input, that's the predicted labels from the test set. Then this print message here is just printing out of sample accuracy. So that's the accuracy calculation here. Then what we also does is that we also want to apply the ML analysis function as we did before for the depth level equal to 3 scenario. So that's pretty much this cell here. So now let's execute the cell. But we can already see that the value in adding complexity is actually marginal, because you can see that so it's positive but marginal. So you can see that the out-of-sample accuracy here is 0.525. And actually, if you go back to the previous cells, the out-of-sample accuracy where the maximum depth is equal to 3 is actually just slightly lower, like 0.523. So something like that. Also, the investment performance doesn't change too much as well. It might be the case that we have some like sort of overfitting here. So we can try to avoid that overfitting. Let me scroll down a bit. So one way to reduce the overfitting risk for decision tree algorithm is that we can play with the hyperparameter called mean sample lift. This mean sample lift, this hyperparameter is able to sort of avoid the overfitting risk. So let me expand this further. Here we're just plotting the tree with depth level equal to the optimal level again. So let's just plot that out. Then here, actually, I don't think those two screenshots, I don't think those two are from the results here. Anyways, I think Marco perhaps stole this from somewhere else, or like maybe this is from old data. But anyways, let's just use those two screenshots to illustrate the overfitting risk and also the role of this mean sample lift. So a form of overfitting risk here in the decision tree is that we might be building nodes to explain the performance of very few observations. So for example, like this node here, we are merely expanding 0.1% of the total data set of the observations. And then actually we are splitting the node again, creating even smaller leaves, even smaller leaf nodes. So of course, to avoid such nodes, we can try to decrease the depths, right? But the thing is that if we decrease the depths, we might be ending up with underfitting. So because as you guys can see, when we increase the depth level, our out of sample accuracy does increase, right? Though marginally. Now to avoid such overfitting risk appearing here, like appearing in this particular example node here, what we can do is that putting restriction on minimum number of samples in the leaf node. So here, if we are specifying that the minimum, sorry, that's actually should be percentage, not really number. So here, if we are specifying that the minimum percentage of samples in each leaf node is going to be 0.05, so essentially 5%, then we sort of avoid this type of overfitting risk here. Now let's execute the code again. So here we are even using a depth higher than 5. We are using a depth that is equal to 7. And we are setting minimum sample size of the leaf node to be equal to 5%. And then we are just fitting that newly defined classifier, which is CLF for leaf. So we are just fitting that classifier to the training set, so X train and Y train. And then we are plotting out the figure. And then this section of code here is just doing the prediction. And based on the prediction, we are calculating the accuracy score. So both in-sample and out-of-sample accuracy scores. So the in-sample is stored in IS accuracy, and out-of-sample is stored in OS accuracy. We also printed out those two variables, and we also calculated the 10-fold cross-validation score, and also printed that out as well. Of course, we plotted the tree as well. So we are using tree.plot_tree to sort of creating a figure for the decision tree trained by us. So if we execute that code, so our out of sample accuracy is 0.526. If we compare that with, say, like the optimal depth situation, that's actually even higher than that situation, than 0.525. So this improvement in the out of sample accuracy is merely because we played with this hyperparameter here, because we restricted the minimum sample size of the leaf node. Let's just wait for the tree figures. Yeah, the tree figure is out now. So as you guys can see, so for the leaf node, the minimum size is actually exactly 5.0% here. So that's pretty much the effect of this hyperparameter here. So it's for avoiding overfitting. So that will kind of like improve your model performance. Yeah. By improve model performance, I mean improve your out of sample performance, because you are like avoiding the overfitting risk. You are avoiding the risk that your algorithm memorize the training set too well. So it's purely memorizing the training set instead of really learning and discovering the real pattern. Now let's also take a look at this figure here. So for this figure, it's essentially a more specific illustration of the effect of that hyperparameter called mean sample slip. We don't have code for this figure here, so this is only for illustrative purposes. So as we can see, for the lower depth levels, that mean sample length, this hyperparameter is actually going to reduce out of sample accuracy. It's understandable, right? So for the red line, that's a classifier with the mean sample slip specified. And for the blue line, that's a classifier without the hyperparameter specified. So if you compare these two, you will find that when the depth level is low, that hyperparameter is not going to improve the out of sample performance actually. So that's because for those relatively low depth levels, we actually don't have much overfitting risk. We actually have underfitting risk. And also we know that the mean sample slip is just used for decreasing such overfitting risk. But here for those low depth levels, we don't have to avoid such overfitting risk because we don't have such risks. So that's why it has no effect of improving the out of sample performance. So it fails to improving the out of sample performance. And then if you move further to the right, so when the tree depth levels keeps increasing, now we do have overfitting risk. So now the hyperparameter, the mean sample slip, will be effective. So it will be effective at reducing overfitting risk, and hence it will be effective at improving the out of sample performance. So the red line is above the blue line.